Hello everyone. In this video we're going to look at some more Chapter 8 examples. Remember, these are inferences involving one sample. My name is Fred Rispoli and I'm coming to you from Stony Brook University. So in particular we're going to look at examples involving proportions. This will be covered in examples 1, 2, and 3. And examples involving variances covered in examples 4 and 5. And once again, these are based on frequently asked questions and frequent errors that occur on test results. So just a quick summary of what we've been working on here with hypothesis test and inferences in general. Remember, we're assuming all the underlying sets are normal. When we think about one sample inferences, which is what Chapter 8 is all about, we covered inferences for means in the first video. In this video, we're going to look at inferences for proportions and variances. Just a quick review of some of the key formulas. When we want to put together a confidence interval for the population proportion, we have a formula that looks like this. P hat is our sample proportion. We get our critical values from the normal distribution, so we have these terms z alpha over 2, and then the square root p hat times 1 minus p hat over n. N is our sample size. And one should check that n times p hat is greater than or equal to 10, as well as n times 1 minus p hat is greater than or equal to 10. Because these are conditions that make the normal distribution really a good approximation for a binomial distribution. And we have a random variable here that is actually a binomial random variable. But we do this to sort of convert this so that we could take advantage of the normal distribution. Another pair of formulas that will be useful are these formulas for sample size. We have, in the first case, this is what we use when we have when we do have an estimate of the proportion. The second one is what we use when we have no idea of what the true proportion may be. So we just sort of said p equal to a half. In that case, 1 minus p is a half, so we get a half times a half is a quarter. And this will actually maximize the value we get for n. So I may sometimes call this the conservative formula for sample size. And finally, we have the hypothesis test statistics. We're doing hypothesis tests for proportions. You can see we get a z. P hat minus p0. P hat is the sample proportion. The p0 is the hypothesized proportion. In our first example, let's suppose that we know during a recent cold season, 42 people caught a cold out of a random sample of 500 in a certain city. We're asked to find a 95% confidence interval for the rate of people who caught a cold in the city. So here's the solution. We begin by calculating p hat. P hat is the number of successes over n. 42 over 500. Expressed as a decimal, we get 0.084. We're given alpha is 0.05. So we start out here by calculating the error term. Right? We want to find our confidence interval. Here's our formula. So we're going to have our sample proportion, which we know up here is 0.084. And then we subtract the error term and then add the error term to get our confidence interval. So to find the error term, we use z alpha over 2. So alpha over 2 is 0.025. The z-value comes from a normal distribution table. We want the z-value that would leave an area of 0.025 to the right. So if we have 0.025 to the right, we would have 0.975 to the left. So we try to get as close as we can. We see we get an exact match here, 0.975. So the corresponding z-value is 1.9, and then up here we get the second decimal place, 0.6. So we get 1.96. So that's where this value comes from. When we calculate the bounds given in this formula, we get 0.084 minus 0.024, and then 0.084 plus 0.024. Simplify, our 95% confidence interval is 0.06 to 0.108, or if you want 6%, the lower bound, 10.8% would be our upper bound. In the second example, we look for sample sizes for proportions. So the idea is, let's say we have a medical study for proportions is to be designed to estimate the population proportion P having a certain disease. How many people should be examined if the researcher wishes to be 95% certain that the error of estimate is below 0.1? Okay. In case A, we assume we have no prior knowledge about the value of P, and in case B, we're given that we have an estimate, the proportion is known to be about 0.2. So we have a formula for each of these. In the first case, we use what I call the conservative formula, and this is the sort of the maximum value for n, given this value for e and z alpha over 2. So our alpha is 0.05, z alpha over 2.025. Just like in the first example, we have 1.96. E, the maximum error, was given to be 0.01. So we would determine what we get from this fraction, square that value, and then multiply by a quarter. We end up with 96.04, but n must be an integer, and we want n to sort of guarantee a certain error value. So we have to be conservative here when we round off. We would round this up to 97. So we get a sample size of 97 will give us the maximum error that was stated. In part B, we're given that, suppose the proportion is known to be about 20%, 0.20. So we could use this formula instead, right? The difference is right here. We have P times 1 minus P instead of a quarter. So P is 0.2, 1 minus P is 0.8. We would multiply that out. We have this term. It is similar to what we had up top. Work out this fraction, square it, multiply by these values here. We get 61.47, and the same rounding rule applies. This gets rounded up to 62. And just notice that, the 62 is much less than the 97, and that should always be the case. The value that you get from the conservative formula sort of maximizes this calculation when we let P be our variable. In the third example, we're going to run a hypothesis test for proportions. So suppose in a randomly selected sample of 100 students in a large college, 14 were left-handed. Now we have a few questions here. The first, does this provide strong evidence that more than 10% of college students in America are left-handed. Let's test this using alpha is 0.05, and we'll use the 5-step method. Okay. We'll come back and answer a couple related questions once we finish part A. So with our 5-step method, we begin by identifying the null and the alternative hypothesis. Here, the null hypothesis is that P is equal to 0.1. So this is the percentage of students that are lefty, 0.1. The alternative would claim that P is greater than 10%. We're using alpha 0.05. That's our level of significance. The test statistic for a one-sample proportion test looks like this. We get P hat, the sample proportion, minus P0, that's our hypothesized proportion, and then that's divided by this term that you see down here. We could identify the rejection region. First, we have to note that we have a right-tailed test. Right? Up here, this tells me I have a right-tailed test because we're looking at P greater than 0.10. We look up the critical value using a normal distribution table. We want the Z value that leaves an area of 0.05 to the right. So if we leave 0.05 to the right, that would leave 0.95 to the left. We try to get as close as we can to 0.95. And notice that we have 0.9505 here, 0.9495 here. So 0.95 would be exactly in between. So these values that we get here would be 1.64 or 1.65. What people do with this is they use 1.645. So go exactly right in between. So that is our critical value. Next, we look at our P hat. P hat is X over N, so X is the number of successes, or in this case, the number of people that have the medical situation. So we get 14 over 100, 0.14. So in our numerator, we have 0.14 minus the hypothesized proportion, which is 0.1. So we get that from right up here. This gets divided by 0.1 times 0.9, right? We're substituting into this formula over 100. So when we work this out, we see that Z is 1.333. That's less than our critical value, 1.645. So the statistical conclusion is do not reject the null hypothesis. What about the p-value? Okay. Well, we have 1.333, so we'd like to know the area to the right. But when we use the table, we get areas to the left. So first, let's look up the area that we would get corresponding to 1.333. So here I've indicated, look at the blue circle. So 1.33 would be, here's 1.3, 1.33. We get 0.9082, but this is the cumulative distribution function. So this is the area to the left. If we want the area to the right, we have to look at 1 minus 0.9082. We get 0.0918. So that would be our p-value. We observe that the p-value is greater than alpha. Right, alpha is 0.05. So that just confirms we made the right decision here. Do not reject the null. And as a summary statement, in the context of the problem, we could say there's not enough evidence that more than 10% of college students in America are left-handed. Okay, so we have a question, part B, asks, what type of error can be made when we do this, right? Let's go back here. In part A, what type of error might you have committed? Okay, so that's question B. Question C, what's the type 2 error rate of the test concluded in part A? If the true proportion of left-handers is 0.13, and we still have the sample size of 100, that's the original sample size. So to answer B, we could say that a type 2 error could be committed because, remember, our answer was failed to reject the null hypothesis. Okay, so we do not reject. So if we look in this table that we had seen in an earlier chapter, our test concludes do not reject the null. We could come over here. In that case, we could make a type 2 error. Okay, we either get it correct if H0 is actually true. Our conclusion was do not reject. In that sense, we got it correct, but there's a possibility here of a type 2 error. And then in part C, we're essentially asked to find the probability of a type 2 error if the true proportion is 0.13. Okay, so we use this notation. We want to find beta, the probability of a type 2 error, if the true proportion is 0.13. So we have a formula that looks like this. Okay, once again, P0, that's the hypothesized proportion, but this P prime, that's the true proportion, okay, 0.13. And then we have this formula Z alpha times this term here you see in the square roots. So we could substitute in the values, and you may want to stop the video right here. This is good practice. Z alpha is similar to what we sort of used before. We have 1.645, and the rest is just working this out. Here with the hypothesized proportion, and down in the denominator for what we're saying is the true proportion. So when we simplify this fraction, and let's round off to 2 decimal places so we could use our normal distribution table, we get phi of 0.58. All right, now where is that and what probability do we get from that? Well, oops, let's go up. We look at 0.58. You see that the probability that we get is 0.7190. So that's a left tail probability, which is what we want. So when we work this out, we get this 0.7198. So that's a fairly high probability of making an error. What people do from a practical point of view, if beta is too large, it simply tells us we need a larger sample size. Okay, so next we'll focus on inferences for variance. There's a couple of formulas here that we need. So for the confidence interval of a population variance, we use n minus 1 times the sample variance over this value we get from the chi distribution. This is the value where we have an area of alpha over 2. This is alpha over 2 to the right, and degrees of freedom is n minus 1. And then the upper bound, we have a slightly different denominator. This is the value you get from the chi-square distribution, where you have 1 minus alpha over 2 to the right, same degrees of freedom. So in general, the chi-square distribution is not symmetric, right? It's not symmetric. The normal distribution was symmetric. The t-distribution was symmetric. But this one is not symmetric, so we get different values in the denominators here. And when we have a hypothesis test to run involving a variance or a standard deviation, we have to use this chi-square test statistic, which is n minus 1 times the sample variance over the population variance. We'll use these formulas in the next two examples. Let's begin by looking at a confidence interval for variance. Suppose we have a random sample of size 12 from a normal distribution. And let's say we know that we got a sample mean, 62.5, and a sample variance of 1597. We're asked to find the 95% confidence interval for the standard deviation. Notice this is the population standard deviation. Okay, so notice a couple of things. First, we really don't need the sample mean, but we have it. Okay. Second, make sure you pay attention to what you're given. Here we're given a sample variance. Okay, we may need to use a standard deviation, so it's always very important to pay attention as to whether you're working with the variance or a standard deviation. Remember here, we want a confidence interval for the standard deviation. All right, so as we begin, okay, we must remember to use the chi-square distribution. Our degrees of freedom is n minus 1, so we get 12 minus 1 is 11. And the sample standard deviation is the square root of 1597, so 39.96. So our formula for a confidence interval for a standard deviation, right, we have to take square roots. If we look at the formula that gives us a confidence interval for variances, so our formula looks like what you see here. Okay, our sample standard deviation, 39.36, right? That's what we calculated here. N minus 1 is 11. Now I need to find values from the chi-square distribution. This first one is alpha over 2. So I want the chi-square value of 0.025. And you also should note a 95% confidence interval implies an alpha of 0.05. So if alpha is 0.05, alpha over 2, 0.025. So let's check the value that we get. Degrees of freedom is 11. So if I have 0.025 in the right tail, degrees of freedom is 11. The value that I would get would be here in my red circle, 21.92. So you can see that's the value that we have down here in the denominator. Okay. Notice this larger value in the denominator will end up giving us a smaller overall value. So this will be our lower bound for the confidence interval. The other value that we need is the value that leaves 0.975 on the left. Okay, so 0.975, we find that up here. and then we come down. Degrees of freedom is 11. So you see that this value is 3.816 or 3.82 if we were to round that off, which is what we did over here. So when we simplify the fraction, take the square root, multiply, we get 67.81. So our conclusion would be that there's a 95% probability that the true standard deviation is between these two values. In our last example, we're given that a hospital administrator believes that the standard deviation of the number of people using outpatient surgery per day is greater than 8. A random sample of 15 days is selected. The result gives a sample standard deviation of 11.2. So whereas at, once again, alpha equals 0.05, is there enough evidence to support the claim? Assume the variable is normally distributed. Okay, so you can see claim is greater than 8, 11.2. It appears plausible that the claim is correct, but it's hard to come up with correct answers with just an eyeball test with this. So let's set up our hypothesis test. We use the 5-step method. The null hypothesis is that the population variance is less than or equal to 64. Okay. Notice here I'm expressing this in terms of variance. In the problem, it was given in terms of standard deviation greater than 8. Here we're saying the variance less than or equal to 64 in the null, and in the alternative hypothesis, which is the claim, we're saying that the population variance is greater than 64. We're given alpha is 0.05. The degrees of freedom is 15 minus 1, so we get 14. So now our test statistic is, chi-square is n minus 1 times the sample variance divided by the population variance. The rejection region is a chi-square greater than or equal to 23.685. So let's check that out. You can see over here, if we use this chi-square table, we need to find the value that leaves 0.05 on the right. Okay, so here we get, for 14 degrees of freedom, 23.685. So that's where this value comes from. Now we go ahead and do the calculations based on the sample data. So our value for chi-squared is 15 minus 1. The sample variance is 11.2 squared. Remember, we were given that right here. You have to keep in mind that we're given S. S is 11.2. So up here we get 11.2 squared. Down here in the denominator, you could think of this as the hypothesized variance, which is 64. So when we work out this fraction here, you have to square, multiply by 14, divide by 64. You get 27.44. So we have to compare that to this critical value, 23.685. We see it's greater, so therefore we reject the null hypothesis. Right, the 27.44 lands in the critical region. so we reject the null hypothesis. In step 5, we need to talk about the p-value. So what's the p-value? Well, using a table, we can't get an exact p-value, but we can get an estimate, right? The idea is to think about what we got in our test statistic, 27.44. Remember, degrees of freedom is 14. So I would scan through this row and try to get as close as we can to 27.44. I notice it's in between these two values, 26.119, 29.141. So this tells me if I come up top here that the p-value is between these two alpha values. So my p-value is between 0.025 and 0.01. This is actually smaller, so we would write that as this type of statement. P is greater than 0.01 but less than 0.025. Okay, the key is that P is less than 0.025, so we know that P is less than our alpha value for sure. So that confirms that we reject the null hypothesis. So here's a case where P is low, the null must go. Finally, we could write a summary statement here and say that there's enough evidence to support the claim that the standard deviation is greater than 8. Okay, so this concludes the video. I hope you learned something through it.